This lesson concerns the derivative and the slope of a graph. And in particular here, I want to start off by talking about the tangent line to a graph. There's a connection here that you'll see as we go through this. Calculus includes the study of rates of change of functions, and the tangent line to a graph is connected to a rate of change, and we're going to talk about that. We know from algebra that the slope of a line indicates the rate at which the line rises or falls. In fact, some of you have probably called the slope rise over run. That's a rate of change, how much it changes horizontally versus vertically. But for a line, that slope is the same at every point on the line. It doesn't change. But for other graphs, the rate of change, or another way of saying it, the rate at which the graph rises or falls can change from point to point. So the rate of change is not the same everywhere on most graphs. For example, if we take this parabola, you can see that I've labeled 4 points on that graph, and the slope of the tangent line is going to turn out to be our measure of rate of change, and it varies from point to point, unlike on a line where it's the same all the time. It's pretty obvious from just looking at the graph that the parabola is rising more quickly at the point x sub 1, y sub 1, that lower left-hand point, than it is at x sub 2, y sub 2, the next one, or at x sub 3, y sub 3, which is at the vertex of the parabola. As we're moving from left to right, the rate of change is leveling off. It's very steep at x sub 1, y sub 1. And as you move around to the vertex, the rate of change goes to 0. And as you pass the vertex and go to the point x sub 4, y sub 4, the rate of change becomes negative and is falling off. As I said, and maybe you would have guessed on your own from this previous example, to determine the rate at which a graph rises or falls at a single point, we're going to use the slope of the tangent line at that point as the measure of rate of change. Want to be a little more formal, we could say that the slope of the tangent line to the graph of a function f at a point p, x sub 1, y sub 1, is the best approximation of the slope of the graph at that point. Because the tangent line approximates the slope of a graph at a point, the problem of finding the slope of the graph at the point becomes one of just finding the slope of the tangent line at the point. So one of our focuses here is to be able to take an equation and find the slope of the tangent line to any point on that curve. Here's an example. Suppose I wanted to find the slope of the graph f of x equal x squared at the point 1, 1. You can see a portion of the graph displayed on the right. The function itself, f of x equal x cubed, is labeled, but at the point 1, 1, the tangent line is drawn in. Now that tangent line has a slope, and the slope of that tangent line will be our measure of the rate of change in that graph at that point. And if you look at it, you can see just by looking at the graph that, and we're talking about the tangent line now, not the curve itself. The tangent line itself, if you move over 1 unit to the right from that labeled point 1, 1, and then 2 units up, you're back on the tangent line again. That should remind you of finding the slope of a line, things you've been doing in algebra for years: rise over run, change in y over change in x, delta y over delta x, however you've described it. That's nothing more than finding the slope of a line. So again, at the point 1, 1, the slope of that tangent line is 2 over 1, which is just 2. And again, we call it the slope. We describe it algebraically sometimes with the symbol dy over dx, which is read change in y over change in x. Sometimes we call it rise over run. But in any case, it's just the same old slope of a line that you've been doing for years. Now, I want to go through this briefly. We're not going to have to do this sort of thing much or maybe at all because we're going to find better ways, but I do want to at least, if nothing else, just for informational purposes and for documentary purposes, show you how this result is derived. And as it turns out, later on, we're going to find better ways to do the calculation. But I do feel the need to at least go through it once to see what would happen if you didn't have these shortcut formulas that we'll come up with later. So anyway, getting back to this problem, if you've got a graph and you're looking at a point x comma f of x, remember f of x is just another name for y, and you move a certain distance delta x to the right and delta y up, you get to another point on the curve. And that's called a secant line, the line that goes through those 2 points. Now, another way of writing delta y is just to say the change in y, f of x plus delta x minus f of x, and you can see it labeled on the graph. But the bottom line is, if you take that second point and compute the slope, what you end up with, and I don't necessarily want to follow it through step by step, but what you end up with is this equation that says the slope of the secant line is equal to f of x plus delta x minus f of x over delta x. And remember, it's really just rise over run, change in y over change in x, and we've written out what the change in y really is. So I didn't really go step by step through the derivation because it's not important to what I'm getting at for our purposes, but I do want you to see that that equation is easily derivable from the graph that we have pictured there. The beauty of this procedure is that you can get better and better or more accurate approximations of the slope of the tangent line, which is what we're really after, by moving those 2 points closer together. In other words, taking secant lines where the 2 points are closer and closer to each other. So for instance, in this original drawing I've got, you can see that you've got delta x being a certain distance to the right. But what if we decrease it? What if we let delta x get smaller? Well, what the effect of that is it pushes the points closer together. So instead of the points being this far apart, putting delta x to be a smaller value, it has the effect of drawing those 2 points closer together on the graph. If you just keep pushing that point, that second point, closer and closer to the original point, eventually you can't even distinguish the 2 points from each other, and at that point you've essentially got the slope of the tangent line. So in the limit, and that's the reason we've studied limits, in the limit as delta x goes to 0, that second point merges with the first point and the secant line turns into a tangent line. And that's the big idea. And that leads to this definition. If we take the limit of that difference quotient, or that rise over run, however you want to say it, as delta x goes to 0, we actually get the exact value of the slope of the tangent line. And this definition is just documenting what we just did in that graph. To get the slope of the tangent line, we take rise over run, and then take the limit of that as delta x goes to 0. In other words, as those 2 points come together. You might call this a derived function because we did a lot of work to get the result. And that gives this expression its name, and its name in general is a derivative. So what we're calling the slope of the tangent line has a more general name called the derivative. And you will be using the word derivative the entire semester. Notationally, if you've got a function f of x and you want to indicate its derivative, which is, by the way, the slope of the tangent line at the point x, at the point where the x-coordinate is x, you write down the name of the function, which is f. you put an accent symbol there beside the f, and you read it as f prime of x. Now, there are some other notations, and we'll talk about them, but that's the standard notation for a derivative. You take the name of the function and you put an accent symbol on the name of the function. So if a function is f of x, its derivative is f prime of x. I want to work an example of using this definition to find the slope of the tangent line. Keep in mind, though, as I said earlier, we're going to find formulas that allow us to bypass this method. This is a very simple function, and as you'll see, the algebra is still not bad, but it's quite a lot of algebra. But luckily, we have an array of formulas that will allow us to find derivatives without having to ever use this. But I want to go through at least one example, just showing you what you would have to do if you didn't have the shortcut formulas that we're going to get later. So let's take this example. Find the slope of the tangent line to the graph of f of x equal 12 minus x squared. Well, the first thing you have to do is write down the formula. The slope of the tangent line is given by that limit. My suggestion, because of the ease of making careless mistakes, is to sort of take bite-sized pieces of this and do the calculation in pieces. And the first big piece is this f of x plus delta x. So I would actually go off to the side, do that calculation, and then take it and put it back into that formula. So if we go off to the side and calculate f of x plus delta x, when you're evaluating a function for some number, you plug the number in everywhere you see an x. But if you take the function and evaluate it at some expression, you just take that expression and plug it in place of x. So what we have to do is we have to take that x plus delta x and plug it in everywhere you see an x in the function. So you're going to plug it in here and here. So you find out that f of x plus delta x is equal to 12 minus, instead of being 12 minus x squared, it's going to be 12 minus x plus delta x quantity squared. And if you watch the preliminary algebra video that I've been promoting since before classes started, you'll know that you'll have to square that binomial by using the formula a plus b quantity squared is a squared plus 2ab plus b squared. So I'm going to do that where in this problem x is like a and delta x is like b. So you plug in that formula and you end up with x squared plus 2x delta x plus delta x quantity squared. Remember, the x is playing the role of a in the formula and delta x is playing the role of b. Now you have to distribute the minus sign. Be very careful about writing this out and using your parentheses and brackets so that you can do this without making careless mistakes. Now you have to distribute that minus sign. So the x squared becomes minus x squared, the 2x delta x becomes minus 2x delta x, and the delta x quantity squared becomes minus delta x quantity squared. And now you have x plus delta x, and now you can put it back into the original formula on the left column. Remember, we started off on the left column, we moved over to the side to do the piece that was the most difficult. Now we can plug it back in. So if you take that f of x plus delta x that I just wrote down and plug in the calculation that we just did, and then you take the f of x and plug in what that's equal to, which is 12 minus x squared, and very carefully do the arithmetic, you'll notice that you've got a 12 here, and you've got a minus another 12, that's going to be 0. Those will cancel out. And you'll have an x squared, a minus x squared here, and you're going to have minus a minus. Remember, those two signs are going to make a positive, and you're going to get a plus x squared and a minus x squared. So in the end, when you do that simplification, the 12s go away and the minus x squares go away, and all you're left with up top is the minus 2x delta x minus delta x quantity squared all over delta x. Now notice there's a delta x in the denominator, but there's a factor that's common to both terms in the numerator of delta x, which can also be factored out. So if you factor a delta x out of that expression, then those delta x's can cancel. And when they cancel, your whole expression just reduces down to the limit as delta x approaches 0 of the quantity minus 2x minus delta x. But remember, we're doing the limit as delta x goes to 0. So if you let delta x be 0, we end up with the final result that m, the slope of the tangent line, is minus 2x. And that's how you do it using the definition. Now it turns out, before long, we're going to see a formula that allow us to do this very quickly, almost just by looking at it without having to go through all that algebra. But right now, this is what we have. We have the definition and we used it. It requires a lot of care, a lot of consideration with being careful with your algebra, being careful about your signs, taking one step at a time, but you will get the results if you're careful. Lucky for us, later on we'll have a shortcut formula that will allow us not really to have to do that. But I did want you to see it done at least once. But before we leave this problem, let's take that result and go further with it. So what we just found out is that if you have the function f of x equals 12 minus x squared, that the slope of the tangent line is minus 2x for any x value on the curve. So I can ask some other questions. For instance, I could ask you, well, what is the slope of the tangent line to this graph at the point 3, 3? Well, once we have the slope formula, calculating the actual specific slope at that value is as easy as just plugging in. So you take the slope value that we worked so hard to get, and notice that it's just -2 multiplied by the x-coordinate of whatever point we're talking about. Well, the x-coordinate of the point is 3, so you plug 3 in for x, and you get -2 times 3, which is -6. So what we've done here is we've taken a fairly simple function, and we've taken the definition of finding the slope of a tangent line and done all the algebra and showed how you can crank out the result. But once you get that result, it's very easy to evaluate specific slopes at specific points on the curve. The big picture here, though, is that once we move into the next discussion, we'll find that there are easier ways of calculating, and that'll make our lives easier. But in the meantime, pay close attention to everything we did. Try to understand how we related the rate of change to the slope of a tangent line. That's the most important thing, that the rate of change in a function is related to the slope of the tangent line. Earlier, as we were working with a method of finding the slope of a tangent line to a curve, we defined something called a derivative as a limit of this expression, sometimes called a difference quotient. I want to pick up from there and continue talking about the idea of a derivative because we will be using it from now to the end of the semester. It's a very important idea. And it's based on this limit definition that we derived earlier. In terms of some terminology, the process of finding derivatives is called differentiation. And if a function has a derivative, the function is said to be differentiable. So add to your vocabulary: derivative, differentiation, differentiable. As you've already discovered, computing derivatives using this formula that we are displaying here can be tedious and time-consuming. It usually requires quite a bit of algebra. Fortunately, we won't have to do it that way from now on because we're going to learn some rules that allow us to bypass the tedious formula. Before we tackle these derivative formulas, though, it might be a good time to mention that there are various common notations for derivative. The idea of differentiation, finding derivatives, slopes of tangent lines, all that was developed over a long period of time by various people in various countries, and the notation was never really consolidated. So you'll see various notations for derivative, and you'll get used to that, but do take note. We've already introduced the notation with the accent symbol, or sometimes I call that the tick mark. But there are others. If you write dy over dx, that means you're asking for the derivative of some function y with respect to the variable x. If you call the function y and you put the tick mark on it, you can say y prime. You can take the function name and put d over dx in front of it. That means derivative. And in some cases, you can just take the function name and put capital D subscripted with an x, and that means derivative. So if you see any of these things, you know that you're being asked to find a derivative. Now let's just jump right into it and learn these formulas that will give us a way of avoiding doing these things by definition, which requires a lot of algebra. Of all the derivative formulas that you'll learn this semester, the one that will be by far the most useful is this one. You need to practice this over and over again until you're absolutely an expert at it. It's called the power rule for derivatives, and it simply says if f of x is a function of the form ax to the n, then f prime of x, that is the derivative, is a times n raised to the power of n minus 1. Now this is very simple, but you need to make sure you understand what it's saying. It says if you start off with a function of the form ax to the n, to get the derivative, you don't have to use that formula. All you have to do is take the coefficient a and the exponent n and multiply them together. That becomes the new coefficient, the coefficient of the derivative. And then you have to go into the x to the power and drop it down by 1. Again, make sure you understand what you're going to do here. You're going to multiply the a and the n, the coefficient and the power. That becomes the coefficient of the derivative answer, and then you reduce the power from n to n minus 1. In other words, you drop it by 1. Very simple, but extremely important. Let's do an example or two. What if I give you the function f of x equals 2x to the third and ask you to find the derivative? If you try to use the definition, it would be a long algebraic calculation. With the formula, all you have to do is remember the process. You multiply the coefficient and the exponent together, and that becomes the coefficient of the derivative. And then you write down the base, which is the x, but you reduce the power by 1. So the 3 gets reduced down to a 2. And you should be able to do that in 10 seconds or less. It saves you so much work. Make the power rule your best friend because you're going to use it over and over and over again. Another useful result is that for expressions that contain multiple terms, the derivative can be taken by doing it term by term, and that's a nice thing to know. So for instance, if I have a bunch of things strung together with pluses and minuses, I can just do them term at a time using the power rule or whatever rule that applies later to them. So I can take derivatives term by term. So if I want to take the derivative of that 3-term expression, I start off with the first term, which is 2x cubed, and I apply the power rule. The power rule says to take the 3 times the 2 and get 6, and then drop the 3 down to a 2. In other words, it's the problem we just worked above. But now you've got 2 more terms. So you've got a plus sign, then you move to the second term. The second term is 4x to the 5th. So what do? Apply the power rule again. 4 times 5 is 20. And you would drop the 5 by 1 and it becomes a 4. So the second term derivative is 20x to the 4th. Then you have a minus sign, and then you move to the third term. 3 times 2 is 6. Then you drop the 2 down to a 1, so you get minus 6x to the 1. And of course, you don't need the 1. An exponent 1 is understood, so if you want to write it as x to the 1, of course you can, but you don't really need the 1 there. And that's all there is to it. You should be happy to have a formula that saves you so much work. How about this one? If f of x is equal to 2x to the minus 1 plus 3x to the minus 3, then the derivative is, again, it's a 2-term expression, so you can take the derivatives term by term. Start off with the 2x to the minus 1 and apply the power rule. The power rule says that you multiply the exponent times the coefficient, so that's minus 1 times 2, that gives you minus 2. And then you subtract 1 from the exponent. Well, if you take minus 1 and subtract another 1, you get minus 2. Then you've got a plus sign and you want to move to the second term. Well, the second term is 3x to the minus 3. So when you multiply the 3 times the minus 3, you actually get negative 9. So that plus changes to a minus. And you subtract 1 from minus 3, and minus 3 minus 1 is minus 4. Simple enough, but you do need to practice. Get rid of all your little trivial mistakes. Make sure you understand the power rule and how to apply it. Now, the ones we've done so far are the simplest possible examples of the power rule. You couldn't get much simpler than what we've done so far. But let's bump it up a little bit and look at some problems where maybe you have to either think or work a little bit harder. And maybe you have to rewrite something a little bit or something like that before you can actually apply the power rule. So we're going to bump the level up a little bit. An example of that would be if y is equal to 1 over x to the fifth, then what is y prime? Well, first thing you've got to realize is that 1 over x to the fifth needs to be rewritten so that it fits the power rule. The power rule has to do with something where you have x to a power. So you've got to think of that 1 over x to the fifth as a negative exponent. Remember that 1 over x to a power is just x to that negative power. So in this particular case, 1 over x to the fifth will be x to the minus 5. Now you can apply the power rule. And remember, if there's an understood 1 in front of that coefficient, so that's like 1 times x to the minus 5. So the power rule says you take the minus 5 times the 1, you get minus 5. And then you subtract 1 from the exponent. So minus 5 minus 1 is minus 6. Simple enough. How about this one? If y is equal to 2 over 3x to the fifth, then y prime is what? Again, you need to rewrite this so that it fits the form of the power rule. And I'll mention once again the importance of having gone back and watched the video that I did on algebra basics, preliminary stuff that's important to doing well in this course, and things like this problem is tackled there. You have to be able to look at that and rewrite it as a negative exponent. So what you need to do is think of that x to the fifth in the denominator as x to the minus 5 if you move it up. So the 2 stays where it is, the 3 stays where it is, the x to the fifth in the denominator moves up and becomes an x to the minus 5. Now technically you could put the minus 5 right beside the 2, but for our purposes it would be better to write it like this because now it looks just like the power rule. So applying the power rule, you take the minus 5 times the 2/3 and you get minus 10/3, and then you subtract 1 from the minus 5 and get minus 6. Here's another. If y is equal to 3 times the square root of x, then y prime is what? Again, that doesn't look like the power rule, but if you remember that a square root is a 1/2 power, then you can rewrite it and realize that the square root of x is x to the 1/2. And once you do that, you now see that the power rule applies. So you multiply the 1/2 times the 3. And then you subtract 1 from the exponent. Well, what is 1/2 minus 1? 1/2 minus 1 is 1/2 minus 2/2, which is negative 1/2. And this one, y is equal to 7 times the square root of x over 8. What is y prime? Again, that doesn't look like the power rule, but if you think of the square root of x as x to the 1/2, you can rewrite that as 7/8 x to the 1/2. And once you do that, you can see the power rule does apply. And you multiply 1/2 times 7/8 is 7/16, and then you subtract 1 from 1/2 and you get negative 1/2. Practice makes perfect, but if you don't get good at these basic ones that we're getting early in the course, if you're struggling with these and don't get that under control, can you imagine what kind of trouble you're going to be in later on when we bump up the level of difficulty? So do not hesitate to spend as much time on these basic ones as you need to be sure you're good at them and can do them rapidly and accurately, because once we bump up the level of difficulty, if you're still struggling back here, what chance do you have to get the ones that are at a higher difficulty level? So take this very seriously. Let's spend a little bit of time doing a few more of these with radicals. I'm going to just sort of do it this way, listing the original function how you might have to rewrite it to take the derivative, then what is the derivative, and if necessary, simplifying it a little bit. So let's do a few of those. Let's start off with the function y is equal to the square root of x. Well, remember, that's just x to the 1/2, and the power rule says you multiply the coefficient, and again, you can think of that as being an understood 1 times 1/2, and then you reduce the power by 1, and so you end up with 1/2 times x to the minus 1/2. And that really doesn't need simplifying. WebAssign accepts that as a perfectly good answer. If you wanted to simplify it, get rid of the negative exponent, turn it back into a radical, WebAssign would also accept that, but WebAssign does not force you to simplify any further than that. Another example. 1 over the quantity 2 times the cube root of x squared. Well, again, you have to turn that into something that looks like the power rule. So I want to rewrite that cube root of x squared and think of that as x to the 2/3, but since it's in the denominator, when I move it up, it becomes x minus 2/3. This is the kind of manipulation that you have to get used to and get good at. If you get stuck on these little algebraic manipulations, then how are you ever going to get the calculus part right? Because going from that step to that step is algebra. It has nothing to do with calculus. But now that we've got it in the form of the power rule, we can take the derivative by multiplying the exponent times the coefficient and then reducing the exponent by 1. So you're going to get minus 2/3 times 1/2, and then you're going to take 1 away from negative 2/3. Well, negative 2/3 minus 1 is the same as negative 2/3 minus 3/3, which is negative 5/3. And to simplify as much as you need to, all you've got to do is multiply the 1/2 times the negative 2/3, and you can see that the 2's cancel out. And you get negative 1/3 x to the minus 5/3. And again, WebAssign will accept that answer. You do not have to simplify it further. Another example. Y is equal to the square root of 2x. And remember, the 2 is under that radical as well, not just the x. So you have to treat those as a grouping. So that will be the same as the square root of 2 times the square root of x. The square root of 2 is just a number. So that's a number times the square root of x. And remember, the square root of x is x to the 1/2. Now it looks like a power rule problem. A number times x to a power. The power rule says you multiply the coefficient times the exponent, and then you reduce the power by 1. So if you take minus 1/2 and subtract 1, you get minus 1/2. And finally, just multiply. Remember, when you're multiplying fractions, it's top times top, bottom times bottom, and square root of 2 is like square root of 2 over 1. So you end up with square root of 2 over 2 times x to the minus 1/2. Before we continue, it might be a good time to look at a couple of special cases of the power rule where you can just call it a power rule problem, but it's such a special case that you almost want to think about it as its own thing. One special case is when the power of the power rule is just 1, when n just happens to be 1. Well, if n happens to be 1, that just means you've got x to the first power, which is just x. So an example of that might be something like, if f of x equals 3x, then what's the derivative? Well, if you actually apply the power rule, you would think of that as 3x to 1. So by the power rule, you'd take 1 times 3 and 3, and then you reduce the power by 1, and you get x to the 0. But remember, any non-zero number raised to 0 power is 1. So you really just get 3 times 1, which is 3. So when you look at it, you can see that if the function is 3x, the derivative is just 3. So in general, if you've got the derivative of a number times x, the derivative is just going to be the number. And if you think about it, that makes perfect sense because y equals 3x is just a straight line with slope 3, and the derivative is the slope of the tangent line. So in a lot of different ways, that makes perfect sense. Second special case is if the exponent is 0. If you have x to the 0, well, x to the 0 is just 1. So you just really have a number by itself. So you have 3 times 1 is just 3. So if you take the derivative of a number, what's that derivative? Well, again, if you want to really think of 1 as being x to the 0, you could think of that function as being 3 times x to the 0. And if you apply the power rule there, you'd multiply 0 times 3, which is 0, subtract 1 from the exponent, get minus 1, but 0 times anything is 0. So the bottom line is, if you take the derivative of just a number, you're going to get 0. And again, that makes perfect sense in the context of what you know about a derivative is giving you a slope of a tangent line. Y equal 3 is a horizontal line, and a horizontal line has slope 0. So the bottom line is the two special cases of the power rule, you can just look at it and see the answer. The derivative of number times x is just a number. The derivative of number is 0. Those are the two special cases of the power rule that you probably just want to sort out and think of in their own rights. So to summarize what we've done so far, you've got the power rule, and then you've got those two special cases. So this is a good thing to focus on to make sure you understand what we've done so far in this discussion. We basically come up with a power rule and then two special cases which might be thought of as rules in their own right. And remember that you can take derivatives term by term. So if you've got a bunch of terms strung together, you can do each derivative term by term. This is a very good thing to put into your notes, to put in one place so that you can go back and refer to it later very easily. Let's do some more examples. If f of x equals 1 over x squared, find the derivative. Well, by now you've probably got the drill down. You're going to write 1 over x squared using negative exponents. So that'll be x to the negative 2. Then you apply the power rule. The power rule says to take the coefficient, which in this case is an understood 1, and multiply it by the exponent, and then reduce the power by 1. Should be old hat by now. What if f of x equals 1 over the quantity 2 times the cube root of x? Well, again, we've done one similar to this. You know you're going to take that cube root of x and write it as x to the 1/3. And since it's in the denominator, it's going to come up as an x to the negative 1/3. So the cube root of x is x to the 1/3, but it's in the denominator. So when you push it up, it becomes x to the minus 1/3. Now it looks like the form of the power rule. Applying the power rule, you get 1/2 times minus 1/3, and then you reduce the exponent by 1. So if you take minus 1/3 and subtract 1, remember 1 is 3/3, so you get minus 4/3. Now about this one. You've got to make it look like the power rule, but this is a product. It's the product of 2x minus 1 times x plus 1. Now later on, we'll actually learn something called a product rule that will allow us to take derivatives of products, but right now we do not have such a thing. So the only way we could possibly handle this is to multiply everything out using the FOIL method and then simplify it term by term. So if you do first outer inner last and simplify the middle terms, remember the minus x from the 2x makes 1x. You get a simple expression that you know you can take derivatives term by term. So you start off looking at the derivative of 2x squared, which is 4x. The derivative of x is just 1. And the derivative of a number is always 0. So the derivative is 4x plus 1. Think about that. Make sure you're good with it. You multiply it out, simplify it, then take derivatives term by term. And notice that the power rule and the two special cases allow you to get 4x plus 1 as the answer. Well, this is actually a quotient, and we don't have a rule that tells us how to take the derivative of a quotient. We don't have it yet. So right now we have to do something different. And there's a trick here. I hesitate to call it a trick. It's just basic algebra. Whenever you have a multi-term expression in the numerator divided by one term, you can break it up into 3 different fractions. It's just the reverse of adding fractions with common denominators. You combine all the common denominators on one denominator and add or subtract the numerators. Here you're just going backwards. So whenever you see anything like that with a multi-term numerator and only one term in the denominator, the trick is just to break it back up into 3 individual fractions, and 3 in this case because there are 3 terms. So you can take the x and divide it into the 6x squared. You can take the x and divide it into the 9x, and you can take the x and divide it into the 5. And then simplify it. X goes into x squared and leaves x, so you've got 6x in the first term, going from here to here. And then when the x's cancel out in the second term, you just get minus 9, and then you just want to rewrite 5 over x as 5x to the minus 1. Now you have that in the form that you can take the derivative term by term using the power rule. So the derivative of 6x is going to be 6. The derivative of a number is 0. And then the power rule says you take minus 1 times 5 and get minus 5 and drop the exponent by 1 and get x to the minus 2. So if you leave out that 0, you get an answer of 6 minus 5x to the minus 2. How about this? Find the slopes of the graph of y equal x squared at various different values of x. Well, that's easy if you understand what the slope is. The slope of the graph means the slope of the tangent line to the graph, and the derivative is the slope of the tangent line. So all you got to do is take the power rule and use it on x squared, and you get a derivative of 2x. And then just plug in those various numbers. So you want to plug in a minus 2, and what do you get? If you plug a minus 2 into the derivative, you get minus 2. In there, you get minus 4. Then you want to do the value at minus 1. Do the same thing. You take the derivative formula, plug minus 1 in for x, and that gives you a minus 2. Then you want to do 0. So you plug 0 into the formula, and you get 0. Plug 1 in, and you get 2. And you plug 2 in, and you get 4. So that's just a little bit of practice of applying what the derivative gives you. The derivative gives you the slope of the tangent line, and you were asked to find the slope of the tangent line at various points here. Find the slope of the tangent line to the graph of g of x equals minus 1/2 x to the 4th plus 3x cubed minus 2x at the point minus 1 comma minus 3/2. So here we're asked to find the slope of a tangent line to another graph. Again, the logic goes, the slope of the tangent line is found by doing the derivative. So the first thing we want to do is take the derivative of that g function. Well, that g is 3 terms. Just do it term by term. So you take the power rule to the first term, and you multiply the exponent times the coefficient and reduce the power by 1, and you'll get minus 2x to the 3rd. Then you move to the second term, use the power rule, and you'll get 9x squared. And then you move to the third term, and the derivative of 2x is just 2. And you have the derivative. But we want the derivative at a particular point. But remember, the value of the derivative is only determined by the x. So all you have to do is take minus 1 and plug it in for x, and that'll tell you the slope that the problem is asking for. So all we have to do now is plug minus 1 in to the formula we just derived from the derivative, and we'll find out, doing all the arithmetic, that the slope of the tangent line to the graph of g of x equals minus 1/2 x to the 4th plus 3x cubed minus 2x is 9. Practice makes perfect in all this. Basic ideas: derivative of the slope of the tangent line. The derivatives we're doing here can all be done by the power rule. And then you practice over and over again as you get really good at it. And that includes changing radicals to fractional exponents and changing negative exponents to positive or vice versa. All the little algebra related to doing those things, you need to practice it. Let's look at this one. Find the point at which the graph of the function y equal x squared plus 10x has a horizontal tangent line. I think the most urgent thing to pull out of this problem is what it means to have a horizontal tangent line. A horizontal tangent line is a horizontal line, and a horizontal line has a slope of 0. So probably the most important thing to pull out of that problem, at least initially, is the fact that they're asking you to find where the slope of the tangent line is 0. But the slope of the tangent line is given by the derivative, so we want to know when is the derivative equal to 0. So we take the derivative, set it equal to 0. So if you read that problem through, you have to pick out the fact that they're asking you for a 0 slope by phrasing it as a horizontal tangent line. Horizontal tangent line means 0 slope. So take the derivative, easily done by the power rule, 2x plus 10, and set it equal to 0. Solve for x, and you'll find out that x is equal to minus 5. Now they asked for the point. Well, the point has an x-coordinate and a y-coordinate, so once you get the x-coordinate, you still have to find the y-coordinate. How do you do that? You plug the minus 5 back into the original function for y and find out what y is. So if you plug minus 5 in there, you're going to get, squaring the minus 5, you get 25. Minus 5 times 10 is minus 50. 25 minus 50 is negative 25. So the point we're looking for is the point minus 5 minus 25. So in going through all these, we've introduced the power rule, which is a big algebra saver in doing derivatives. We've reinforced the idea that the derivative gives you the slope of a tangent line. And we've also practiced rewriting things so that they fit the power rule. You've got to be good at all those things. Remember, this is just the very beginning of our work with derivatives. And if you're struggling with this, it's going to affect you the rest of the semester. So take whatever time is necessary to get these things to the point that they're just second nature. Doing the simplifications, doing the power rule, doing all these little things, they have to become second nature so you'll be able to tackle the more difficult stuff later.